CVPR Part 4. I'm discussing 3 papers. One is by Chelsea Finn, and this is Open VLM. Chelsea gave a presentation where she made a case for basically a new kind of workflow in robotics, which is akin to the large language model workflow, and that is you pre-train on internet scale data and or robotics data, and then you fine-tune and you're able to generalize across tasks, modalities, and embodiments. Then I'm going to present 2 very related papers, actually. I would say they're almost the same thing. Darrell, Trevor, and Ilya R, both at Berkley, and they both work together, so that's why. The fundamental idea here is to use the transformer-based architecture for robotics learning and to define the robotics problem as token prediction, and tokens being sensory motor tokens. So in other words, the token here is either a sensor data point or a motor data point. I'm going to describe in details what that means. And the sentence prediction. So if we use the analogy of large language models, then predicting the next word and predicting a sentence is predicting sensory motor action. This is not even on podcast. It's July 7, 2024. This is Cryptalco. It's a Sunday. There's no update for the year. We're up 23.5%. The market's up 16.5%. We're outperforming by 7%. So I'm continuing now my series on CVPR. Like I said in the previous episode, I've taken a break because of the essay that we published, that was published actually just recently, about trolley economics. It's on YouTube, but not on our website yet, but that's going to change today. So now I'm continuing with CVPR, and I think for new listeners, I just want to reiterate the importance of these types of events for us. The purpose of this podcast series is to give people a sense for what it feels like to run a hedge fund. And we at Orange Capital Partners, we are actually running a hedge fund, and for disclosure purposes, this is not meant to solicit any kind of investments or anything like that. Our fund is closed, and if you want to contact us, please don't use this platform. But again, our fund is closed, so there's no solicitation or anything like that. This is really an educational podcast. Education hopefully helps anybody who's interested in listening, but also us. We keep record and we calibrate our thinking by doing this type of education. Now, what does it mean to get a feel for what it feels like to run a hedge fund? Well, it's really in the words of what it feels like to run a hedge fund. So this is not a blueprint of how to run a hedge fund, because there is none. And this is not a task, 6 points of how to get rich or any of those things. I think it would be ludicrous for us to do something like that. And it would be the exact opposite of what we actually believe in, which is, a hedge fund it's like art. It's like making a movie. It's something that you can't learn, something that you can't potentially be born into or anything like that. Most hedge fund managers desperately try to give their funds to their offsprings, and very rarely actually that works. The same way that the kids of Giacometti are probably not very good sculptors, and Picasso's kids are probably not very good painters. So it is just what it is. And that's why we're emphasizing what it feels like, right? What it feels like is it's not a sort of frontal cortex logical derivation of the logical step that it takes to make money with a hedge fund, because it's a lot more than that. And it's really difficult to put it in a closed-end, concise version of words. And we hope that over the years, our episodes can give a summary of what the actual process is like. And for people, we have about 3.5 years worth of episodes now on our website. Feel free to go and listen to all of them. They're all free and available. Maybe in summary you can get a sense for what this is all about. So now let's get to the point here. We're talking about CVPR. That's a conference. The actual name is Computer Vision and Pattern Recognition, but those things don't matter that much. It really is about computer vision, and in these days it is of course about AI. Now it is focused on computer vision because computer vision is one of the most successful subplots of AI, if you will. And second, there is really a massive opportunity now for robotics to take advantage of computer vision in a whole new way. And this is what both of these papers are about. And this new way, the way we see it is the following. We see it as the ability to, on the one hand, use vision and ground it in text to have more semantic understanding of what's going on, and B, to have text which is augmented by vision to help robots actually do tasks much more efficiently. What do we mean with that? So why don't we start with paper one? So Chelsea Finn introduces OpenVLM, which is short for Open Vision Language Models. What is a vision language model? From a technical perspective, vision language model takes an image, encodes it into a string of information that then gets fed to a large language model, and then combined those two. So when it sees a tree, it knows that this is a tree, and when it sees a cat jumping from the tree, it knows that there's a cat jumping from the tree. Now, let's just take those two examples, particularly the latter one. Cat jumping from the tree, right? There's physics information here. Because cat jumping from the tree, the VLM knows that means the cat is going to go from the top of the tree down to the surface, right? It knows that because that's what jumping from a tree means. Now, does it have Newton's equations and quantum mechanics and whatnot encoded? No, it doesn't, because it's learned that a cat will jump from a tree, and almost in any scenario, at least in this multiverse that we live in, this means the cat will go towards the surface. And this goes back to end-to-end learning and the ability to learn something from data pure. This is what this is all about, right? We don't want to explicitly program anything. And the question that Chelsea is asking is, well, okay, if we don't want to explicitly program, we don't want to have robots tediously going through tasks and explicitly program how to do them. Well, how can we learn, how can we teach robots to do stuff, and then maybe they can generalize, right? I mean, this is the North Star, because that's what humans can do. Remember, we spoke about the Robinson Crusoe robot. The Robinson Crusoe robot is the kind of robot that you drop on an island and it starts figuring out what it needs to do to survive. Like, we're not there yet anytime soon, but we are hopefully getting towards at least a more general version of a robot that can pick up a bottle, that can pick up a knife, that can pick up an egg, and that can throw a ball, but is not going to throw an egg. Okay, that's where we are today. And can we do this with data only? And if so, what's the solution? And Chelsea and co, there's a big co-written, there's a lot of authors on this paper. They have two approaches here. One is an open source VLM. So this is just meant to sort of democratize the actual model and bring a standard in place, because as she says in the paper, there's just too much fragmentation. Every lab has their own VLM. One VLM doesn't work in the other lab, so on and so forth. The other thing, which is as important, is the commoditization of hardware-software architecture model, and of course also inference, right? Because again, we can have the best model in Berkeley Lab A that can't even be used in Berkeley Lab B. Forget about Stanford or MIT. And the problem there is it's just not scalable. It's not transferable to other labs. So they're trying to mitigate both of these things with some help from Google. There's the open, I think it's RTX, open data set. I'm getting confused, RT1, RT2, RTX, but the idea is that you have data sets of robots doing tasks in different labs across different modalities using the same, at least the same backbone architecture. This is the fundamental idea, and they're taking this further by having an open source VLM using also commoditized hardware and software and architecture. So we can start scaling up things, and we can also leverage the community and the creativity of an open source community. This is really what this all comes down to. So this is the paper. I'm not going to go into the technical details. There is always, I highly recommend, particularly people in the industry, to read some of the technical stuff, usually part 3 of a paper, which is describing, let's say, what kind of architecture they use and why, how they tokenize things. The ablation study is also always very interesting. Ablation means, all right, we trained the model now. What if we do it with less data? Or what if we change the parameters or freeze some parameters? And the way you learn about a model, and in particular, which parts of the model are crucial for the results that you're getting, is by ablation studies. So to summarize Chelsea's paper, again, it's an attempt to open source vision language models for robotics. The idea being that with vision language models, robots can be grounded and have a scalable architecture to generalize over tasks, embodiments, and domains. What I mean with that is domain being kitchen versus factory floor, task is grasping versus cleaning, and embodiments is humanoid robot versus something else, and so on and so forth. Now let's switch gears to Berkeley. There's 2 presentations. Darrell Trevor from Berkeley, a professor, and then Ilya R. He's either postdoc or PhD. I'm going to combine them because to me, they kind of talk about the same thing. And the fundamental idea here is to use the transformer architecture and the analogy of large language models for robotics. What do I mean with that? Well, first, transformer architecture is something that is using the attention mechanism as the backbone for an autoregressive prediction model. So if we take the canonical example of text, so we train a model on internet scale text, we tokenize the model in certain ways, and then we have all these, I think at this point, trillion parameters. We have massive amounts of tokens, and they train cross attention, self-attention. How is this token related to itself, and how is this token related to other tokens across the universe of the internet? By doing so, we are actually able to compress the knowledge of the internet in what's called latent space. So think about it this way. We have the internet, which is the ground truth, and then we have a latent space, which is a much, much, much compressed version of that knowledge in the internet, and then we can extract from there. So of course, there's 2 applications for this. One is inference, so we can learn and do stuff. Second, of course, is compression also. So we could potentially store the whole knowledge of the internet in this latent space, and then ship it to Mars or something, and have that knowledge available up there. So back to this paper. So what they're doing is using this idea of a large language models, which tokenizes around text, and then predicts the next token with the goal to predict the next word, with the goal to predict the next sentence, with the goal to predict the next paragraph. You know where I'm going with this. So how about we use the same thing for robots? But if we did that, what would be the token? What is a sentence? What is a paragraph? What does that even mean? That's what these papers are explaining. And the answer is the token. Okay, the data that is fed is sensory data. So that is vision, maybe haptic information. Just think of any kind of sensor. But for simplicity, let's stick with vision here for a second. So we bring that in, and we also have motor information, which is actuators, proprioception information. So my joint is at this angle and is moved in the next epoch to this angle with this type of force. Those types of things are being tokenized, then trained in a transformer-based architecture, and inference is done by autoregression to predict the next token. Now, the sentence in robotics land is sensory motor token sequence. That's the sentence. This is really what these papers are about. Now, again, I encourage people to go to part 3 of the papers because they talk about the actual technique. And one thing I want to mention for all of these papers, so Chelsea's paper, Ilya's paper, and Darrell's paper, they talk a lot about data curation. And I want to digress here just as a tangent for people that maybe have teenage kids like I have. Just think about a little bit what the future of science will look like. And I think Chelsea's paper actually is key for that, because what she's saying is that her open VLM, which has 7 billion parameters, outperforms other VLMs that have 55 billion, so 10x more parameters. And the way she does that is by feeding the 7 billion parameter model more data, but more importantly, curating the data. And why am I mentioning all of this is Stanford's building a massive data science building as we speak, and it's right next to ComSci and electrical engineering. And as my wife likes to say, this proximity is not just a coincidental thing. This is real. The data science part of the equation is what Chelsea Finn calls data curation. It's, if you will, the boring part, but it's that thing which actually makes stuff work. It is what it is for all the mathematics geniuses and chess grandmasters and all those people who think that just with a blink of an eye and a inspiration they can change the world. That's not how it works. The way AI works is hardcore engineering, data curation. So you have to think about what data are we feeding those robots. The question is, what do I need to teach the machine so the machine can do the task? And the machine wants the data in a clean form. It wants the right data to be able to learn. Right data means, for example, how about we use data in the case of, let's say in the case of Chelsea, she's using visual, internet scale data, actually the same with the Berkley people. So both, all these papers are starting with internet scale data, so video data. And let's just use data where actually action happens. Sometimes, a robot picks up an egg and that's it. So what's one supposed to do with that? How's one supposed to? But the robot picks up an egg and puts it somewhere, or maybe cooks with it. That's much more interesting information, and that yields a lot more inferenceable learning. So things like that, again, I encourage people to go deeper. Of course, these things are always much, much harder to convey in a paper than if you do it yourself. And the purpose of all of this for us is to understand where the science is going, what kind of technologies we can inference from, and also what does it mean for things like hardware, what does it mean for the humanoid robot development that is very dear to our hearts given our positions in Tesla and NVIDIA. So back to the Berkley paper, really key here is, again, we have this idea that we can use proprioception, motor data, sensory data, all that kind of stuff. We can use this as a backbone, tokenize and pre-train a model, and then go from there. This is really the idea, and learn to predict the next token. Learn to predict the next token. And from there, predict the next sentence. And the next sentence is a collection of tokens that are either sensory tokens or motor tokens. So this is the idea. And I think it's hard to it's hard to overstate how revolutionary this could be. Because if this works, if we can parallelize robot learning the same way we could parallelize language learning by dissecting everything into tokens and then run these massive parallel training algorithms across modalities, embodiments, tasks, I think we're onto something. And this is why robotics is the next wave. It's certainly not the only wave. I think language models have a long way to go, but we have this ability now to add vision and semantics to machines and in an end-to-end way train them how to navigate in nature. And the language of nature is motion, and the tokens are sensory and motion tokens. Thank you.